think we can start. Today we're very happy to have Fornal as our speaker. He's currently a postdoc working with Ben Christie in UC San Diego. Among other topics, he's recently working on dark matter, baryogenesis, guts, and even electrolyte PDFs. Although I usually think of him as one of those theorists who actually bothered to look at the nuclear physics archive.
So, thank you very much for the introduction. Thank you for having me. Before start, I have to be before too. Okay, just. I have to get to the experimental part aside.
Oh, sure.
Okay. So it's really great to be here, and yeah, I'll say a few words about a recent idea we put forward with Ben Christie, who is currently the physics chair at UC San Diego, and about interpreting the neutron lifetime discrepancy in terms of a dark sector. And I'm sure all of you will be skeptical about this. I myself am also skeptical whether this is the way nature works, but this path hasn't been explored by anyone before, and it's not experimentally excluded, as I will show. And I think it's nice that it had many theoretical and experimental follow-ups in recent months. So I'll dive right into the details, because you are all very familiar with them, I'm sure. In the standard model, there's essentially just a beta decay channel for the neutron. So it decays to a proton, electron, and neutrino. There are, of course, radiative corrections to this process, with photons being radiated off the quarks or the electron. But all those processes add up to a branching fraction of 100%. So 1 in the standard model. Now, the way it is described is through a decay matrix element, which contains the vector current here, an axial vector current for the neutron, and theoretical calculation, including radiative corrections, gives this result for the neutron lifetime, where VUD and GA have to be determined experimentally. VUD is the first element of the CKM matrix, and GA is this ratio of the axial vector to vector current, which is also extracted from experiments. And if we take the particle data group averages for those numbers, within 1 sigma, we get the neutron lifetime between 880 and 886 seconds, so approximately 15 minutes. A very recent lattice QCD calculation of GA yields this region for the neutron lifetime between 870 and 900 seconds, so the errors are still too big, but probably within 2 years they will get to a percent accuracy. So something to wait on. But it's around 885, but with 1 sigma error this big, it doesn't really say much. So there are 2 types of experiments which measure the neutron lifetime, the bottle and the beam experiments. In the bottle experiments, ultra-cold neutrons are caught in a gravitational trap inside a container, and they are very slow. Like, you can just keep them for more than like 30-40 seconds, and you can essentially put a bottle in and take them out and pour them through a detector. They're that slow. So they are trapped here. Oh, the battery is on. I mean, I'll use one. And essentially they are measured. Their numbers measured as a function of time. And the simple decay equation yields an exponential decay curve, which is the standard e to the minus time over the neutron lifetime. So essentially, the number of neutrons which remains is proportional, the decays is proportional to the number of neutrons in the bottle, and this minus 1 over this proportionality factor is the lifetime. And the curve is fitted to the data points, and the lifetime is determined. This is called the bottle lifetime, and it should give the total neutron lifetime. Because no matter what decay channels it looks at, I mean that the curve gives the total neutron lifetime. Now, the beam experiments are qualitatively very different. They don't fit a curve to data points. They measure the rate of the decay to protons. So there's a beam of slow-moving neutrons. The number of neutrons in the beam, the flux, is being estimated. And then the protons from a particular part of the beam are being trapped, and the rate is calculated. So using this equation, I mean, we would get the beam neutron lifetime. However, if you notice, this is the rate of the proton production, not the neutron here. So if there is a different decay channel for the neutrons, I mean, this equation will not give the total neutron lifetime, but the partial lifetime for the decay to protons. And this lies at the heart of our proposal. If you calculate the beam lifetime from here, it's equal to the number of neutrons they came from over the rate, but it's rate of the detection of protons. So this is equal to the branching fraction of neutron going to protons times the actual decay rate for the neutrons. So the beam lifetime is equal to the actual neutron lifetime over the branching fraction of neutron going to protons and anything else. And of course, in the standard model, this is 1, as we discussed, or 100%, so the two lifetimes are the same. So what do experiments show? The experiments show a discrepancy. Here you can see the green points are the bottle measurements, and the average is given by this green line here, and the average of bottle experiments is 880 seconds. Whereas the beam result is over here. There are essentially two beam experiments which have been performed. It's this point and this point. However, this has been reanalyzed very recently in 2013, and the errors shrunk a little and the point moved a little. So essentially this average here is the average between this beam measurement and this independent beam measurement without this point here. And it's 888 seconds. So it's longer. And this is the way, if I go back to the slide, which if the branching fraction cannot be larger than 1, it's smaller than 1 or 1. So the beam lifetime, if this is supposed to make sense, should be longer. And experiments do suggest this. It's longer than the bottle lifetime. And the discrepancy is 8 seconds between them. So it's approximately a % discrepancy. It's at the level of 4 sigma. So of course, obviously, the first thought is that it's some sort of unknown systematic error which people didn't take into account. Most likely for the beam experiment, because we have so many consistent model experiments. However, what we thought is, well, okay, but perhaps it's not an experimental result. And what then? So we asked ourselves a question: is there new physics which can explain the discrepancy, assuming the experimental results are valid? And the question is yes, and it's based on this relation between the lifetime and the beam lifetime is longer because there are additional decay channels for the neutron. So what our proposal is that this branching fraction is 99% of the total neutron decay channels, and there's a remaining 1% which has been undetected so far. So definitely cannot be standard model particles only in the final state, because it's just beta decays. So it has to have some sort of new particles. If it hasn't been seen, then it should be either only dark particles, or dark particles perhaps in the presence of standard model ones as well. But then, at some point you open the particle data group, and you look at neutron going to invisible, which is the case here, and you see that the lifetime is greater than 6, 9, 10 to the 29 years. And to get a branching fraction 1%, you need 100 times 15 minutes, so approximately 1 day lifetime. So I think many people, perhaps if they thought about it, they just gave up. But there is a way around those bounds from the particle data group and those experiments, namely SNO and TAMU. What they're looking at is a huge collection of nuclei. For example, we have oxygen-16 here. And what they are looking for a neutron disappearing inside this nucleus. Probably this a shell neutron. And when the neutron disappears, the resulting wave function is some new physics state, which hopefully has some overlap with excited states of oxygen 15. And if it does, it will de-excite to the ground state of oxygen 15, emitting a gamma ray with a given energy, approximately 6 MeV. And of course, there could be other decay products what the experiment is looking for. And those limits are based on this. But there actually is a way to not to have this happen and the neutrons still undergo a dark decay. And I will explain this based on beryllium-9, which produces the strongest bound in our model. So of course, beryllium-9 cannot decay to beryllium-8 and a neutron because of the neutron binding energy inside beryllium-9. So here is the energy level. Let's say the energy goes up. So let's say this is the mass of beryllium-9. The mass of beryllium-8 plus the mass of the neutron is higher. So the decay beryllium-9 to beryllium-8 plus neutron is energetically, kinematically forbidden. So let's consider a case where the neutron undergoes a dark decay to a final state F, and see whether it's possible, what to do to forbid beryllium-9 going to beryllium-8 plus this final state. Well, obviously, if this is close to the mass of the neutron, this cannot happen because of the neutron binding energy in beryllium-9. But this doesn't have to be very close, like extremely close to the mass of the neutron. It can be close enough to stay within the range of the neutron binding energy in beryllium-9, so which is 1.66 MeV. So in particular, if the mass of this state is equal to mass of the neutron minus this or less, then this decay won't happen, and the neutron dark decay will take place.
Actually, do you say what is lifetime of beryllium-9 again?
Beryllium,
Yeah, the lifetime?
of which one?
Beryllium-9.
It's stable.
Oh, it's stable?
Yeah. So this bound comes from the stability of only stable nuclei, and this gives the strongest bound. Because from all the stable nuclei, this one has the smallest. Well, it's called, I think, separation energy, neutron separation. So if we look at the numbers, it turns out that the mass of the final state is anywhere between 937.9 MeV and the mass of the neutron. The neutron can undergo a dark decay to this final state, but beryllium-9 and all other stable nuclei will remain stable. Well, this opens the door to a whole new area of model building, namely the neutron could decay to a dark particle and a photon, dark particle, electron-positron pair, two dark particles, and well, you name it. I mean, the model building possibilities are endless. Of course, there are some constraint on the parameters of the model, which one has to check if it's consistent with all other experiments. I will focus on only those two cases, but others will have explored in the literature in the recent month substantially. So let's just think about the minimum possible model. It's probably nature is not that simple, but let's be very simplistic here and assume we just add a dark matter particle, or a dark particle doesn't have to be dark matter. So in order for this decay to happen, the mass of chi has to be in this range I just discussed. And this corresponds to the photon being emitted here to be anywhere between 0 and 1.66 MeV. And it's a monochromatic photon, so it gives a very well-defined signature with photon detector. And in case if you want this to be the dark matter, or at least stable, this cannot decay to a proton, for example, an electron, and this sets a bound on the mass of chi, an additional lower bound which corresponds to this range for the monochromatic photon energies. And this hasn't been looked at before this at all. So I will say about the experimental progress in a moment. But just how to describe it from a theoretical point of view? Well, we write down the effective Lagrangian, effective interaction between the neutron and the photon. Here we have a kinetic term for the neutron, a mass term, and a magnetic interaction term for the F mu nu. So this term describes the interactions of the neutron with the photon. We have a kinetic and mass term for the dark matter, or dark particle, and a mixing term, which will be needed between the neutron and chi. And this epsilon is a model-dependent parameter, which we now use just to describe this process at the effective level, but if we build a particular model, this epsilon will depend on the parameters of the model. So this is the input you get from particle physics. So after diagonalizing the mass matrix, there's an effective interaction term which describes the neutron going to chi and the photon, and one can derive the rate for this decay, which depends on the neutron G factor, or the charge, so it's approximately 4, the electron charge 0.3 in natural units, mass of the dark particle chi, and this epsilon squared, which is model dependent. So in order to show that this is consistent with experiments, we wrote down a very simple particle physics model where the decay of the neutron occurs through a heavy colored scalar phi. So the simplest Lagrangian for this is just phi interacting with two quarks with strength lambda q, with a quark and a dark particle here with strength lambda chi, and that's about it. That's just mass terms and kinetic terms. So by matching this Lagrangian to the one at the effective level, we were able to derive what epsilon is in this model. There's a product of the two couplings here over the mass of phi squared times the matching coefficient, which thankfully corresponds to this relation here and was derived from the lattice. So its value is very precisely determined from lattice calculations. Which were done mainly for proton decay reasons, but the same matrix element enters here, with just it's a down part instead of a huge one. So there's a small difference in the element. So in order to get the branching fraction 1%, so the rate is 1/100th of the neutron decay rate, but we need the mass of this particle chi over the square root of the product of the couplings to be 400 TeV. So this is from this means it's not ruled out by the LHC by any means. Well, because even the future 100 TeV collider might have trouble probing this type of model. So phi in general, it could be produced through this PP collisions, either singly produced or through gluon fusion pair produced. But because of this huge mass suppression, the 2 jets up to 4 jet signatures would be too suppressed for any existing or in the near future collider. There is, of course, a chance that one of the coupling is super tuned, they fine-tuned to be 10 to the minus 12, in which case this could get down to a TeV, and we could see something like 2 jets and missing energy at the LHC already now, but there's no reason, absolute no reason to fine-tune any of those couplings to be that small. So no hope for probing at the LHC, unfortunately. So the other, I think the more interesting case is when the neutron decays to 2 dark particles, let's say a fermion chi and a scalar. It could be also a vector, but we chose it to be a scalar phi for an intermediate, let's say chi tilde fermion. Now the bound for nuclear decays is on the sum of the two masses. If you remember it, on the mass of the final state, so the mass of chi and phi has to be in this range. But also the beryllium constraint sets a lower bound on the mass of chi tilde. Otherwise, the beryllium would decay to beryllium 8 plus chi tilde. So it has to be heavier than 937.9 heavy. But it could be as heavy as we want, 800 GeV, TeV, or only. So in particular, in the previous case, the mass of chi had to be kind of tuned to be close to the neutron mass. Here, they could both be equal to half a GeV, and it will still be fine with the nuclear decay bound, as long as chi tilde is heavy enough. And if you want both of them to be stable, you could have their mass difference to be less than the mass of the proton, less mass of the neutron, but it's not necessary for them to be the dark matter. So how to describe it at the effective level? It's my batteries is ending, but I have spare batteries. An effective Lagrangian can look like this. I have to use my spare battery. So it's the same as in the previous case with a chi tilde instead of chi. And there's an additional interaction term between the three dark particles, chi tilde, and phi. Here, so the structure of interaction is lambda phi, and the rest is exactly the same. One can derive the formula for the decay rate, and in this case, it's a little more complicated because there's an intermediate chi tilde particle. But it of course depends on the values of the couplings. So this depends on the coupling of the three dark particles here. There's a function of the masses of chi and phi over here, and depends on the epsilon, which is a model-dependent quantity. And there are two kind of qualitatively different cases. One is that when this chi is heavier than the neutron, then this is the only big possible decay channel, and its rate has to be, branch fraction has to be 1%. If chi is lighter than the neutron, then there's also a possible decay to a chi tilde and a photon. And there's a competition between the two channels. Well, this is the ratio of the two rates, but they have to add up to 1 to explain the anomaly. So very fast, since this is very similar to what we had before, a UV complete model for this is when phi interacts, when there's a heavy phi interacting with the quarks or in a dark matter, just like before. We have this additional interaction term, and get the decay rate for this model. This epsilon, after matching the two Lagrangians, is equal to essentially what we had before, with a chi tilde instead of lambda chi tilde instead of lambda chi here, and the same beta from the matching. If chi is heavier than the neutron, we again get something which is consistent with LHC and colliders. And I'll explain in a moment why I chose the coupling here to be 0.04. And when it's lighter than the neutron, there's this decay channel and that, and the two should add up to branching fraction 1. So now, why did we choose 0.04? Well, in the first case, when it's just a dark particle and a photon, and we want chi to be the dark matter and thermally produced, that's a problem because we don't have enough freedom to have the right annihilation channels. The annihilation channel is only through a heavy particle here, which is very suppressed. So in the first case, we have to resolve to, just impose non-thermal dark matter production. And a very similar model was proposed for this by one of the locals here. And essentially, we could just take their results and apply them to this model. And so this could be a good non-thermal dark matter production mechanism for the decay of a heavy scalar, such that the asymmetries are for the dark sector and varying sector are produced during the decay and stay like this. There's no interaction between the two sectors. In the second case, we could have dark matter non-thermally produced, like here, but also thermal production becomes available because we can have annihilation diagrams through the intermediate chi tilde particle. And if we choose this coupling here, lambda phi to 0.04, then this gives the right relative density of dark matter. So I think now that I'll start talking about the recent developments around this area and experimental developments, that's essentially what we put forward in our idea. But it turns out to be many branches of kind of physics we didn't expect that come out of this. So I'll start with neutron stars, then go through more complete models of that, baryogenesis and other solutions, and then I'll move to the experiments. So you can imagine how much stressful it was, and we almost got a heart attack the same day, 3 papers came out saying that our model is excluded from neutron stars. Essentially, the titles were "Neutron stars exclude baryon dark decays," or "The neutron dark decays are incompatible with neutron stars." So, but when you got to the last paragraph of each of those papers, there was an assumption mentioned that, of course, it's constructed differently in the PRL versions, that it's for non-interacting dark particles. So whenever interactions are introduced, there is additional freedom which enables one to avoid those constraints. So of course, neutron dark decay changes the equation of state of a neutron star. And so what we thought with Ben is that, well, neutron beta decays, so those decays are blocked in a neutron star. So if it undergoes a dark decay, there will be a gas of fermionic dark matter in a neutron star, and they should also be blocked by Pauli blocking. But it turns out if you do a more careful analysis, it's not exactly the case if there are no self-interactions in the dark sector. Namely, the contribution to the energy density in a neutron star from the dark particle is always larger than the contribution to the pressure. So what happens is the equation of state becomes much softer in neutron stars. So here is an example what happens. So the way one gets neutron star masses is from integrating the Tolman-Oppenheimer-Volkoff equation, which depends on the equation of state. And normally it can yield, of course there's uncertainty, like here there are uncertainties in the assumptions in how the neutron star really works, what are the densities inside the neutron star. But if you take into account the dark decays, the maximum neutron stars turn out to be 0.8 solar masses. And that's a problem because there are 2 cases of neutron stars which were observed with 2 solar masses. And of course, if you raise up the mass of the dark particle, like to 1.2, you can get to 2 easily, but then you won't have neutron dark decay. So that's why the conclusion was that neutron dark decays are excluded. However, if one introduces strong repulsive self-interactions in the dark sector, this is no longer the case, and one can easily get 2 or even more solar masses for neutron stars. And well, this can be done by adding, for example, a dark Z into our model, which induces self-interactions between the dark particles. And it's nice that this was pushed in this direction, since self-interacting dark matter was proposed, as you know, 20 years ago, Steinhardt and Spergel, to solve the small-scale structure problems of the lambda CDM modeling, the missing satellite problem, the Corcus problem. Of course, there are other standard explanations for those inconsistencies, but this is definitely one route which was explored. So soon after this came out, Stein and Fornal, they constructed a model with self-interacting dark sector, which evades all constraints. They looked at neutron decaying to dark matter to a dark photon here instead of the normal photon. So essentially, the effective Lagrangian they wrote is exactly the same as we have the 2 lines here, but they have a gauge U1 group to introduce this dark photon here. So if we have a covariant derivative here, there will be an interaction of the dark photon with the dark particle. And they looked at all the constraints from supernova, from CMB, from BBM, and neutron stars, and they found a region, small, of course, small region, but it's still non-zero region where this model solves the neutron lifetime anomaly and is consistent with all astrophysical observations, including.
Sorry, you can take a step back. I think I'm missing the phase space arguments here. So you're saying like you do, yeah. So okay, so you have no self-interactions. The neutrons are allowed to decay. Neutron decay to dark matter is blocked. Is that what you said?
No, that's what we thought with Ben initially.
That's what you thought.
The only thing about when people wrote down the equations and did a proper analysis, it turns out that they are partially blocked at some, so the neutron star doesn't just come apart. But the masses that it can reach are smaller.
Oh, okay, so you can, okay, so, all right.
You can
a little bit of non-interacting dark matter that you're just allowed.
This is a non-interacting case.
Relatively strong amount, okay, but if you introduce them.
If you introduce some interaction.
Is there like, and maybe you're gonna talk about this, but is there like a very pedagogical way to think about this? Like why you, if you bring in internet interactions in the dark sector, like why does that change the blocking from
Well, it probably just introduces additional terms which make the equation more stiff.
Okay.
So it's like,
it's
more to the energy than
what's happening to the neutron equation state?
So if the dark decays make it more soft, right?
Uh-huh.
And if you introduce some interactions, it will make it more stiff, so it push it up.
The pressure,
You also chose the potential to be repulsive in this case, right?
Repulsive, has to be repulsive, yeah. That's a good point.
So higher pressure then, is that what this repulsive force is getting?
Higher pressure, yeah. So then the neutron star can get big.
Okay, I think that's kind of awesome.
Because so without self-interaction, the contribution to pressure is smaller than the energy density, but the additional terms to the pressure, the self-interactions. And in this case, they also analyzed the case where this could be the dark matter, and the conclusion was from CMB constraints, this one here, it could only count for 10% of the dark matter. But a model where it could be all of the dark matter was proposed shortly after by those two guys. They essentially took our model number 2, neutron going to chi phi, fermionic chi and scalar phi, and introduced a dark Z. To be through covariant derivative of this interaction. This is an effective picture. So it interacts with both the chi's and phi's. And in this case, the chi here can explain all the dark matter in the universe, and then it's consistent with all astrophysical constraints, this model. And at the same time, what is important, it solves small-scale structure problems. So namely the missing satellite problem and the Corcus problem. Of course, this is pretty easy to check whether it solves it or not, because there are papers deriving what the cross-section of the dark matter scattering should be for it to solve this. So they just check that the parameters they used in the model fit the cross-section needed for dark matter scattering. Let's see, but very well recently, this was just yesterday, it was still in archive, but 2 days ago a paper was posted of the same authors that with the dark photon paper, showing that you can get a nice low baryogenesis mechanism through neutron dark matter oscillation. So they constructed a model which can solve the neutron decay anomaly, the lifetime discrepancy, and at the same time explain baryogenesis. So essentially they start off with some, well, that's the assumption. They start off with a dark matter asymmetry, and they show that those type of interaction in the model similar to what we proposed is enough to transfer some of the asymmetry to the baryon set. Another paper proposed this month was this is unrelated to the neutron lifetime discrepancy. What they proposed is that low scale of baryogenesis can be obtained through B-meson oscillation. So there's an initial heavy scalar decays to B and anti-B quarks, and so there's asymmetry produced. They hadronize into B-mesons, and then they decay to baryons and dark particles. And as you see, this is exactly the interaction we had in this model here. It's just that it couples to the third generation and first generation, so we look only at first generation quarks. So in this case, it's a different model without there's also been a proposal to look for not only neutron dark decays, but also neutron meson dark decays. And the model was constructed where there was kind of like a dark copy of the standard model, in which case a neutron could decay to 3 dark quarks, and heavy meson, the K and B mesons could decay to 2 dark quarks, dark meson. And this could be either related to the neutron lifetime discrepancy or not, if the rates are small. And finally, which was my biggest worry about our proposal, is this paper here, which came out relatively, I think, a month or 2 months after our paper, where those guys essentially selected data for measurements of GA, which were taken after 2002. And this selected data set produces a lifetime corresponds to a lifetime which is equal to the model neutron lifetime. So they claim this suggestion that the bottle lifetime is the actual neutron lifetime, not the beam as we propose. But soon afterwards, there were papers which came out which flipped our reasoning the other way. So in our case, it's the beam lifetime which should be given by the standard model, and the bottle lifetime is a result of the additional decay channels. Whereas this paper, for example, says it's the bottle lifetime which is given by the standard model, and the beam lifetime is a result of mirror neutron oscillations in a magnetic field. So the bottle experiment doesn't have magnetic fields, so there's no effect there, but those would have effect in case of a magnetic field which exists in the setup of the beam experiment. And also there was a proposal of using a large interference term, so interference of the standard model axial vector and vector coupling with tensor new physics couplings to also cancel the dark decay contribution to the bottle experiment and at the same time explain the beam experiment. But now, I guess I'll have some time to discuss some experimental things, searches and ongoing proposals, or ongoing also experiments. Starting with the channels we proposed, and then general experiments which might take a closer look at the general neutron decay, not only for specific channels. So within 4 weeks, after our paper came to archive, there was a dedicated search for the photon signature performed by the UCN group at Los Alamos, and they concentrated on the region of when the energy of the photon corresponds to the case where chi is a dark matter. There's only a handful of people who really knew what was being measured. I don't know why, but so this is the result. The initial paper claimed a 4 sigma exclusion in this energy region, and a PRL version claims a 2.2 sigma exclusion. So probably something changed in their analysis.
So what exactly are they looking for here?
They just
neutron decay.
They put a detector around the bottle, the container with cold neutrons, and just looking for monoenergetic photons in this energy range.
That are coming from the inside, not from the outside.
Yeah.
And do they have? Do you know the experimental setup? Like, how do they know if it's coming from the inside or the outside? Again.
That I don't know. They claim they have everything shielded. Like here, if you look at the result, they are the background is in red. So the black is after they subtracted their signal from the background. So there are peaks, I mean, here and there, and this is the size of they took the rate which we predicted, and this is the size of the signal they expected.
It's pretty background down.
Yeah, so for example, here there's a peak I don't know if they understand this now or not, which is much bigger than that. So that's probably why it went down from 4 sigma to 2 sigma. And then within another month, the same group, probably some people were shuffled, looked for the channel with the electron-positron pair, and they were able to totally exclude this particular channel for kinetic energies of E plus E minus greater than 100 keV. But this, we couldn't really construct a nice theoretical model for this signature, so we're not very hopeful that this will show anything. But now help can come from real, well, not real, it's also real, but a different type of nuclear physics, namely from nuclear decay, but unstable nuclear decay. So there are actually many nuclei, unstable ones, which have a neutron separation energy smaller than beryllium-9. So in general, in that case, the dark decays can contribute to their overall decays. Examples are, there are examples all with neutron-rich nuclei, like hydrogen-7 and lithium-11, beryllium-11. So there's a lot of. In our paper, we noticed that, and we proposed to search for this in the case of lithium-11, which would probe dark decays for a dark particle in the mass range from the lower bound of beryllium up to the mass of the neutron minus this neutron separation or binding energy. So it wouldn't probe the whole parameter space, but the smaller the neutron binding energy, the bigger the parameter space which those experiments would probe. From lithium-11 would decay to dark decay to lithium-10, or some excited state of lithium-10, dark particle, and then it would just decay to lithium-9. But it was pointed out here there are pretty short lifetimes, like 100 milliseconds, so it would be hard to detect. And especially there's a big background from beta delayed deuteron emission from lithium-11 in this case, so this would be swamped in the background. So there's a paper which came out which suggests to look for dark decays in beryllium-11, which has a separation energy of half an MeV, so it would probe the whole parameter space within up to half an MeV below the neutron mass. And the decay would go through some beryllium state and excited an off-shell chi tilde, for example, and then it could go to the two dark particle final state, which we propose. This will be a way of looking for it in pure dark decay case. And what makes it more exciting is that there was an experiment performed 4 years ago by this group here. And what they looked for is they found an unexpectedly high number of beryllium-10 nuclei in beryllium-11 decays. So what the initial explanation was that there's some sort of narrow resonance which produces a beta delayed photon emission here. So they expected this to be beryllium-10 plus some protons, but they were not sensitive to this final state here. They only could detect beryllium-10. And the rate here was 1,000 times larger than the expected rate from the standard model. And those authors here proposed that an alternative explanation for this is a dark decay of beryllium-11, for example, this channel. And actually an experiment looking whether there are protons in the final state or not was performed at the end of August this year at CERN in Zolde, and they are still analyzing the data. So we don't know when they will finish, or if it's when they're going to publish their result. On top of that, there are of course ongoing beam experiments at NIST here in the US and in JPARC in Japan. They're getting more and more data, but the first results will be in approximately 2 years from now. So there's still a long time to wait. So what we thought with Ben is, we have a bottle experiment. Well, you can just put in a proton detector or proton detection system inside of this. But then the experimentalist starts saying that it's extremely hard to do this, to measure both the neutron lifetime from the curve and have a proton detection system. But I think there's a proposal they want to put out to start constructing a detector like this inside the bottle experiment. So this would give a definite answer because it will be the same experiment measuring both things, and without the systematics that the beam experiments have. Okay, so I think I can slowly stop here. So I hope I have shown that model 2 we propose is not excluded, as some papers were claiming. And especially if we add, well, we need to add a dark Z, so an interaction, self-interaction between those dark particles, such that there's enough repulsive self-interaction to be consistent with neutron stars. And this would be also useful for other areas of astrophysics. But even if the beam experiments, it will be exciting if they agree with the current beam lifetime. But if they don't, and the value comes down, I guess one could also use, those models to look at neutron dark decays at a smaller rate, which will not be excluded. Of course, the smaller you go, the less excluded it is, but it kind of loses the purpose to look for it if there's no experimental motivation. So let me end with quoting Clara Moskowitz from Scientific American, that missing neutrons may lead a secret life as dark matter, which I think describes well what we wanted to say. It would be really great if the good old neutron turned out to be the particle enabling us to probe the dark sector of the universe, which would, of course, bind even more the nuclear and particle physics communities, which seem kind of separated in recent years. Thank you very much.